Okay, I think we're starting. So let me share my board. So we're gonna wrap up this little lecture series talking about geometry for Eilenberg-MacLane spaces. So wanted to actually get to a relatively new perspective. It's actually not that new. Ravenel and Wilson first developed this perspective in the 70s, um, perspective being revisited, which is Hopf structure on these, and then share a number of questions, some which would merely be looking at standard, known calculations from a new perspective, and some which would break new ground. And I wanted to say that the timing here is with a workshop on Hopf structures about to start tomorrow. This is June 22nd in for me, and I think this workshop starts tomorrow. And if you are interested, oh, I don't know how that got erased. If you are interested, you can email Sarah Peterson. It might not be too late, at Sarah L Peterson at gmail.com. I'm pretty sure those two L's are there. Yeah, she's running the workshop, and she also worked with me a little bit on some of the progress and some of these ideas. She's herself developed Hopf and applied Hopf structures to understand equivariant Eilenberg-MacLane spaces. So that's part of how things are coming back, how these ideas are getting revisited. So let's recall that we're looking at the iterated bar construction. I'm going to drop the deltas in general because, well, that's the model we're using for classifying space. So we'll save our breath. So what we have is a series of points, and then a series of group elements. And remember that what we're looking at is elements of some n cube to the k cross over sk of our group to the k. And what we're going to do is, if I give you k points, and ultimately these can be chosen to be distinct because of our equivalence relations. But what I will do is I can use the SK action to choose these in dictionary order. So I'll just call that, x1 less than or equal to x2. And then the corresponding, so those are the underlying points, x1, x2. And then the labels are abelian group elements, and I'll go ahead and then label them accordingly, A1, A2, etc. Okay. And right. And then there's a couple ways you can see that there's a natural cell structure around. One is just that this is a sort of a realization of a multi-simplicial complex, but and multi-simplicial complexes, they have cells. They're governed by the combinatorics that that I'm gonna share now, which is that so cells are indexed by, I can produce an n-1 tuple namely, so here we have that xi and xi plus 1 share their first di coordinates. Okay, so these non-negative tuples are going to tell us, x1 and x2 are bound together with one coordinate or should share three coordinates. So they're going to be on a plane or a line, or in higher dimensions, you can have higher codimension subspaces. And we can call these either iterated bar cells or actually they coincide with a cell structure that is studied in configuration space theory, namely Fox-Neuwirth cells. Okay. And then for G equals the cyclic group of order 2, our homology classes of this BNC2 are in one-to-one correspondence. The basis for them is in one-to-one correspondence with n minus 1 level dyadic forests. And let me review sort of how that goes and elaborate a little bit more. So one thing is that for G equals the cyclic group of order 2, our labels can omit the group labels, because if any of them is the trivial element, the identity element, that point can be omitted from the configuration. And then you would just have labels of G, G. So that's no information, so to speak. And so, right. So we would have, for example, this forest. These dyadic forests are symmetric, so the valences at every level are the same, and then they're powers of 2, hence dyadic. So here's a little example. And yeah, to give you an idea of how you get an actual homology class from this, I claim that if I look at the first tree, I have 4 points which share 2 coordinates. So the number of coordinates you share is given by the level there. And so that means the first, second, third, and fourth all share their coordinates. All right, I'm going to give you these Ds. In fact, let me often use square braces for these Ds, so I'll continue to do that. And then there's another group, but then they share just one coordinate with another group of 4, which shares 2 coordinates. And then they don't share any coordinates with the second group of 2 points, which which also share 2 coordinates. Okay. And that itself is not a cycle, but if you shuffle things with respect to the zeros, you do get a cycle. And these, the claim is that these are the representatives of homology. So um, if we think about it at the chain level, even the degree of one of these cells is going to be um, well, the default degrees of freedom is for every point in the configuration, say there's k of them that has in degrees of freedom, but then these shared coordinates are restricting degrees of freedom, and so we just subtract those. So they're naturally a codimension. And then the multiplication of these forests is sort of union, but as a divided powers algebra. So for example, our class above times another class where um, just to give you a reminder of the variety of what these things can look like, you just take the union of all of these, but because I have a repeat between the two the same tree appearing in the same forest, I'll get a coefficient of 2 out front in this case, which is 0, of course. Right. So this is just the statement. Now I have to distinguish between sort of what is known. So the algebra presentation is due to Cartan, and then these particular chain reps are let's just call that a still unpublished or conjectural. It's closely related to work that collaborators and I have done in symmetric groups. And Chad Juicy and I wrote a paper on Fox-Neuer cells and started to prove some things along these lines for a similar calculation that arises in the cohomology of symmetric groups. But we haven't sort of elaborated everything, and in particular in this context. So anyways, so Cartan in the 1950s, you use the fact that you're really looking at, there's a spectral sequence with Tor over the homology of G, K, K, converging to the homology of BG. That's really, we haven't talked about the relationship of the bar construction to homological algebra, but you're geometrically realizing this standard construction for resolutions over the group ring, and so it's immediate that you're really just looking at Tor over the chains of G is what the homology is, so to speak. And so you can look at the spectral sequence. He shows that it collapses, and he also shows that when it's divided powers coming in, when this homology is divided powers, you get divided powers coming out, and then you can keep track of dimensions. So this implies that it's a divided powers algebra with generators in these dimensions. The chain representatives are, let's say, conjectural. Again, that's what we kind of mean by geometry here, is conjectural, but based on similar results for cohomology of symmetric groups. Now, maybe I'll take the opportunity to say a little bit of a digression that we talked about BG last time. Elementary, just you can take any contractible free G space and quotient by the G action. So for S in, well, S, remember, like the cyclic groups would act on infinite spheres. S in acts on the space of in points in R infinity by permuting labels. But in points in R infinity, you calculate the homology of these configuration spaces, and they start in degree n-1. So this has no homology, no fundamental group, so it's contractible. So implies that BSN is the space of unordered configurations in R infinity, unlabeled collections of points. And then remarkably, at the prime 2, the Fox-Neuwirth cell structure is basically, additively, but after some radical regrading, isomorphic to the for configurations, these iterated bar. Yeah, and let me be clear. I meant the chain complex rather than. So that's a remarkable fact, kind of a little known fact, that there's this additive isomorphism from the cohomology of symmetric groups, which has to do with kind of Dyer-Lashoff operations, to the homology of the iterated bar complex, which also has to do with like Steenrod operations. But it's yeah, these remarkable those are known to be related in other ways, but in this case, kind of a remarkable duality is one thing you need to do. The Fox-Neuwirth chain complex is on the one-point compactification for unordered configuration spaces, and basically what happens there is there's a point at infinity, a formal point at infinity, where two points without labels, when they collide, they just go to the point at infinity. That's just, standard one-point compactification definition. Whereas in the iterated bar chain complexes, 2 points, collide, and then they add to the identity. And so yeah, basically it just so happens that different rules lead to the same cell structure in these cases. Right. So that's kind of a recap and elaboration on some things we've done so far. But let me now start talking about a key additional piece of structure noticed about 20 years after Cartan's calculation. And for this, we need our group to actually be a ring. we can ponder this for non-commutative, but we'll stick for sure with commutative. Namely, our iterated bar construction has a multiplication arising from the multiplication. Remember, it has these are topological abelian groups on the nose by union, so to speak. But here the picture is that suppose I've got a point here labeled by ring element R, another point S, maybe 3 points U, V, and W are ring elements. And what you do is you just look at the products of those points in the higher dimensional cubes. This is another time where it's helpful to use cubes because then these products work out cleanly. And we're going to use our multiplication. So this will be R times U, S times U, R times V, S times V, R times W, S times W. Okay, so that's all you're doing. Note that this is non-commutative because, well, we fixed a cube and the thing would be, I don't know, rotated, reflected if I chose the R and S for my last coordinates as opposed to my first coordinates. So this induces a product on homology, and this is studied by Ravenel and Wilson, although they Milgram studied a similar structure, not on Eilenberg-MacLane spaces, but on some other infinite loop spaces, also related to symmetric groups, actually. Right. So what's one key example? So let R be Z mod N or Z, or really, I guess any, yeah, doesn't have to actually be one of those. So there's a class B in H1 of BR with, you know, again, maybe with R coefficients if you want, where now my generator, instead of just calling it A or G, I'll call it 1, sort of takes a trip along the interval, okay? And then the claim is that circ with B is an example is often called the suspension operator. Because, for example, you know, if I have this in H2 B Z2, then this circ B is going to be this class where these 2 points are on a line, but then that line can move, and that's in H3 B squared Z2. Okay, so you're just taking your class and you're letting it sort of be swept out in one direction in the next higher dimensional cube. You know, by the way, a good then B circ with itself k times, or let me say n times, is what's often known as the fundamental class. Just where one point takes every possible value with label 1, okay, in the ring. In our leveled trees, it is this simplest tree with no branches, but in -1 um, uh, levels. Right. And in our graphical basis, moreover, um, what it does is it's just sort of oh, it graphs a root. So um, I mean, you have to then think about what you get when you're trying to graft a root for something which is not symmetric. But again, I'll leave that as a question, some details to work out in this theory. Um, right. So we've got this product, the circle product, the suspension, as a special case. And then Ravenel and Wilson say that our usual product and the circle product and the diagonal map on homology, which is the standard coproduct, they form a Hopf ring, and this is on the homology of all of the iterated bar constructions of all of these Eilenberg-MacLane spaces. So what is a Hopf ring? A Hopf ring is a ring object in the category of coalgebras. And what that means is that you have two multiplications and a co-multiplication, and each multiplication with the co-multiplication are bialgebras. And then there's this distributivity axiom that if you are doing a circle product over a star product, so this is a times product over a plus product, then what you get is you can distribute, but you need to do the coproduct and use that coproduct to then produce things which multiply. So this is sort of what distributivity means for ring objects. And by the way, in this terminology, a Hopf algebra really should be called a Hopf group because it's a group object. So you would have this multiplication with a co-multiplication, it's associative. You have inverses, that's the involution of a Hopf algebra. A bialgebra would just be a Hopf monoid. So, but these are Hopf rings. So the proof that this forms a Hopf ring is a pretty easy diagram chase, which let me just tell you about. So what we're thinking about is these multiplication maps. So you do the star multiplication, or the usual multiplication or the union multiplication, and Then you do the circle product. And then the point is that you're going to get the same result if you first apply the diagonal. And then then of course you need to rearrange things. I won't put that reordering step. Um, but then right, we multiply each of these. Um, and then with the circle multiplication, and then we do the star multiplication, and you trace through things. And the circle multiplication is again this Cartesian product. The star multiplication is the union, and you're basically this commutes because if I take two copies of the same uh, configuration, that's what delta is doing. And if I take something which comes as a union, and I'm taking a Cartesian product with a union, it's the union of the Cartesian products. And we teach that in basic proof courses. I did that this term. So that's actually what comes down to showing that this is a Hopf ring. Um, but the calculations require knowledge of coproducts, and that's maybe trickier than you might think. And it's not impossible, but you need more machinery than we've done so far in this lecture series. A lot of these product structures were cellular. They're given by unions of things. It was pretty immediate to reason about. This coproduct, you either want to develop some Hopf algebra machinery to tell you about what can be happening in the product side. Um, and then maybe you need to do a little bit more arguing once you have that in front of you, or you can kind of switch to cohomology. But even that's a little tricky. I mean, and again, the point is that that immediately, like for example, the diagonal copy of RP3 inside of RP infinity is homologous to, well, a copy of RP3 in the first factor, a copy of RP3 in the second factor, and all copies RP2 cross RP1. Um, that's something that again we can know from cut product. We can kind of we could try to do it a little bit more directly with maybe pairing with cohomology, but that's still and then it still becomes an intersection calculation. But in any case, it's not immediate from things that we have in front of us. Um, right. So then what Ravenel and Wilson show once you have this machinery, and they were interested in this machinery to do calculations far beyond, they weren't just revisiting Cartan, but they were making new calculations for other cohomology theory, other homology theories, and other infinite loop spaces. But they, um, but in their language, the homology of these b to the n z mod 2s is generated as a Hopf ring by these classes with 2 to the I points. So these are H 2 to the I B C2. Well, what's pretty immediate then, um, So a corollary of that is that uh, with divided powers, it's all generated by this B class again in H lower 1 of RP infinity, BC2. Because its divided powers are exactly these classes. So if you have a Hopf ring and now are allowing divided powers, then you've got this lovely fact that you can generate all homology of all Eilenberg-MacLane spaces by this simple little class in degree 1. Now, the question slash conjecture, so we're getting to that part of the lecture, is what is the compatibility? What are the relations? When you incorporate these divided powers operations, divided powers for the union product, the plus product, the star. And again, this is something, let me say, so a Hopf ring with divided powers, yeah, let me, well, so give an example first. So I like to do the divided powers as subscripts, just because you then have circ I as a superscript and things get a little less crowded. So B2, but now let's do the circ product with B2. And if you think about it for a second, B2 means I've got two, B divided powers 2 means I've got 2 points that can occupy any 2 points along the line. And same here, and I'm just taking the Cartesian product. So I see all possible rectangles with parallels, with sides parallel to my bounding square. So that's what this homology class is. It's a 4-dimensional class. And then, so this is an H4, B squared C2, the second Eilenberg-MacLane space. And the claim is, and this was proved by Dana Hunter. We were working on this again with Sarah Peterson a little bit too, and others, that this is homologous to. So you would wonder, wait, this wasn't one of the classes. It kind of looks like those classes that we drew, except that these guys have sort of correlated behavior across those two lines. Before, what happened on those two vertical lines were independent. But this ends up being homologous to this class. I just maybe think of it as forgetting 2 of the 4 points. But it's actually, it's tricky. Dana had to think of a few different co-bounding objects to get between them. You might wonder, okay, could I take a pair of corners and let them collide and then they vanish and I'm left with the opposite corners, but we couldn't get such a homology to work. So anyways, and again, this would be this class. So in symbols, that's just B circ B divided power 2. Okay, that's what this class is up here as a tree. So the obvious conjecture is that that if you have compatible divided powers, and if you have divided powers of different types, there's part of the axioms for divided powers says that that, relates a sixth divided power to a second divided power on a third divided power, for example, with some coefficients. But if I've got I-fold divided powers and I take their circ products, I can take the circ product first and then take the I-fold divided powers. Okay. And it might seem obvious that something like this should happen, but this property fails for the cohomology of symmetric groups, which are divided power Hopf-Ring. So in other words, a Hopf-Ring with additive divided powers. But we prove this is, see the 23 paper of Lorenzo Guerra, Paolo Salvatore, and myself. We give an example where we show that this axiom fails, and so it in part makes our statements. We like to have the divided power structure to as another way to produce new cohomology from old, or in this setting, it would be new homology from old. It's a lovely part of the story, and it goes back to Cartan. But when you're then integrating that with the Hopf-Ring structure in the symmetric group case, yeah, the obvious compatibility just isn't true. So yeah, let me actually end with a lot of questions. So again, we'll do the divided power compatibility with the circle product. That's a conjecture up above. Or even, and this again might be in the literature already, what, just developing divided power structure at the chain level. As far as I know, it's well known to be there at the homology level by Cartan's structure, Cartan's results. But here, what we're saying is, if I have a topological, this is say for any topological abelian group, then I can take a simplex cross a simplex, two group cross group, multiply it, and then there should be a divided by two version of that. And so you end up, for example, wanting to identify the right subcomplex of two simplex cross two simplex to do this. This is kind of a funny thing to do. So this is a remark that for an on the nose topological abelian group, things called Dyer-Lashoff Kudo-Araki operations vanish. And this is kind of a substitute for those. You have this very strict condition of being a topological abelian group. Your Dyer-Lashoff operations vanish, but you still have some sort of divisibility in your in your powers, so divided powers. Right. So another thing just close to what we've been talking about is describe this new multiplication. We know what star does. It's union with divided powers. We know divided powers is repeating trees in a forest or repeating a forest. Just describe the circle multiplication in the dyadic forest basis. It's determined by well, I mean, right. You would need sort of this. So some cases are known, but um, if you had this compatibility, could you streamline this description? Right. Getting a little further from things we've talked about, but certainly in this area, something that Ravenel Wilson pay attention to is you have Steenrod, or sorry, Milner's description of the dual Steenrod algebra. Well, the Steenrod algebra is the cohomology, stable cohomology of Eilenberg-MacLane spaces. It's the cohomology of Eilenberg-MacLane spectra. So the dual Steenrod algebra is going to be in here. I think it's the dyadic trees within the dyadic forests, but again, there's lots to be worked out there. And then you would also want pairing with the cohomology. And in the symmetric group case, this would be the pairing of the Dyer-Lashoff algebra with the cohomology of symmetric groups. You end up getting the same pairing at the prime two. And that's something that I've been interested in for a while. It seems like a very combinatorially rich kind of pairing that once you had maybe the right kind of forest basis and for the cohomology, let me give the Dyer-Lashoff picture, which is and you can actually make this the geometry of these classes can be made into cochains for these iterated bar models, but that's highly conjectural. So you often think of something like square two, square one is fairly formal, but there's some geometry there as well. Again, easier and certainly on firmer footing on the homology and cohomology of symmetric groups side. And so we'd want to understand these classes pairing with, well, for example, square one is a picture like this. And exactly one spot do you have 4 points which line up. So there's an interesting pairing to work out there. Then, of course, there's the question of the other primes, the odd primes. There obviously you still have your class B, and then P times B is the boundary of something, and it's not too hard to find it as the boundary of something in this case. There's a few different choices, so I won't elaborate, but you basically take P points and you sort of let them scale and translate. Those are your two dimensions, and you can find P times this. Now, P times this is not the same as B star itself, P times. P is just sort of scalar multiplying. So if you want, you can think of it, well, at the fundamental group level, it's one traveling from left to right, and then traveling from left to right again, and traveling from left to right again. Whereas again, this is defined by union. So it's, this is in particular, this is a class in a higher degree. P times B is still in degree one, but again, it's a boundary. and you can think of it what it's the boundary of, but then yeah, this is just the beginning of the story, but those are two of the more important classes. You ultimately wonder if, of course, it would be nice to have better understanding. I mean, there's still to this day some recent computer calculations that elaborate um, these kinds of calculations, the homology of Eilenberg-MacLane spaces with integer coefficients. But is there a nice description, maybe with some sort of trees? And let me state a conjecture. It's not fully precise, but um, is that higher torsion, all torsion, higher torsion is governed or produced by divided powers operations. So if you take some two torsion um, and you take its divided power, it makes sense that, well, the product would naturally be two torsion, but once that product sort of vanishes and you divide it by two, you get some four torsion. And the conjecture is that this is the main source. And again, I've got some evidence for this back on the cohomology symmetric groups side. Right. And then just to, since I mentioned the homology of symmetric groups, let me just say that again, fill in some history and context, but mention a problem that is out there and would be fun with these kinds of ideas. So again, Milgram first introduced Hopf rings for structure and the homology of, I'll call it BS infinity. It's a little bit of a lie, but maybe, well, group completed, that's less of a lie, but then I want to use, I want to talk about the different infinite loop space structures. And, Ravenel and Wilson were interested in things like Rava K-theory of Eilenberg-MacLane spaces or other infinite loop spaces. And then interestingly, a very different Hopf ring structure was found by Strickland for Morava K-theory and also cohomology of symmetric groups. So, and that's what then my collaborators and I rediscovered. Giusti, Guerra, Paolo Salvatore, and myself, we just focused on the cohomology of symmetric groups. But with one of the goals, and we've sort of worked that out fairly well, but one of the goals is that, and what Strickland did was he worked out, he calculated the circle product in decomposables. So that's, quite the quotient that you're taking when you're taking in decomposables. Any non-trivial circle products you're setting to zero, but it's a was an impressive step. And this is a Hopf ring. And again, we've got now between what Neil did and between using what we do for cohomology symmetric groups, this is ripe for attack, as they say. So anyways, that sort of places some of these techniques in context. Of course, you have things like the equivariant story, but I'm hopefully conveyed in these three lectures that even this classical calculation that Cartan did so amazingly in the 1950s, I think there's some opportunity to revisit it, maybe even better understand the homology of integer Eilenberg-MacLane spaces, which are, I think most people wouldn't be offended to say they're kind of a mess, but maybe with this divided powers Hopf ring structure, the geometry around, maybe we can understand some things better. All right.